Hello, everyone. Thanks for joining for this webinar series. So we periodically try to do free webinars for sharing our knowledge and teams inputs to the industry, to the community. And that's we do at least once in a month. So today's session is going to be on deep learning essentials. Deep learning is definitely becoming very important in the context of generative AI, LLMs, and all of the changes which is happening, the large language models. So it definitely sits in the bigger umbrella of AI and generative AI, very connected to that. So we'll be spending most of the hour dealing with the deep learning essentials. Before we get started, today's session is brought to you by bigdatatrunk. My name is Raju, and I'm part of bigdatatrunk team. We founded this company back in 2008. Our focus is primarily education, corporate education, mostly in technology and soft skills. We do it online and in person to corporates and individuals. Mostly it's become online after pandemic, and that's continued to be, but occasionally we do go to companies and their campuses and universities and so on and so forth. And I'm grateful to be teaching a lot of Fortune 500 companies and great universities as well. These are some of the categories which we teach. Most of them are cutting edge technology, but we have business skills, soft skills, leadership skills, as well as the need of the clients and different requirements keep growing. And that's an area of focus of ours as well. Today's topic is focused, as I said, in generative AI. We have tons of different courses in generative AI, whether it is e-learning format, whether it is in the instructor-led format, virtual instructor-led format, different formats. And as I said, we have been fortunate to be able to teach several Fortune 500 companies, and we do public trainings as well. So individuals who want to continue the journey and kind of build, you can look at our public trainings and other programs. We have some e-learning, different kind of programs and different things which are available. So that's a quick brief about the company, but we'll get started. Today's session is focused on deep learning essentials. It's on the basics and foundations to get started. So you don't need a lot of background to get any input from this. The speaker for today is Aparna. Aparna is one of our lead instructors who is teaching a lot of different things in especially the AI space. She has done a lot of teaching in the academic space, in the corporate space, and definitely continues to build her portfolio as the technology is changing and building on generative AI and different skills as well. So without further ado, I'm going to pass it to Aparna. So let me stop the share. And Aparna, whenever you're ready.
Yeah, hello. Thank you, Raj. Hello, everybody. Good morning, good evening, based on where you're located right now. Welcome to this session on deep learning essentials. Let me share screen and get started. Yeah, before I get started, I just want to make sure the slides are up and visible.
Yeah, I can see presentation mode, the first slide.
All right. Thank you. So, this will be the agenda of the webinar that we have planned today. This is, I would say, more of a beginner intro kind of a session on deep learning. There will be the initial part which will focus on how deep learning has evolved. What is the basic essential architecture that typically goes into a deep learning network? We'll focus very briefly on, exactly what it is that happens within a neuron. When we say that a deep learning network is learning, what do we mean, by that term learning? The next part of the webinar will focus on some of the most common architectures, which are the convolution and the recurrent neural networks. There will be quite a lot of focus on various applications that I think, probably all of us are already using on a day-to-day basis in various different domains. One aspect I would like to make clear, though, is that, this webinar, like both the agenda as well as the description of it says, is mostly about the basic essentials behind deep learning. We do have upcoming webinars that focus exclusively on generative AI and the large learning models, the LLMs as well. But those are topics, for other sessions that are going to happen post this webinar. All right, so let's get started. Why all this buzz, right now in terms of deep learning? Like most of us are aware, artificial intelligence as an area has been around probably, like since the 50s. Man has always had this intent of being able to create machines that can think, and probably, help us out in terms of doing a lot of tasks that are otherwise very repetitive and monotonous for us. And one thing that we definitely notice currently over the last, I would say, 6 to 7 years is that, uh, while the initial intent was to create systems that would help us do the more simpler kind of tasks, these days generative AI based systems are equally good at even, carrying out slightly more original creative kind of tasks. So post AI, it kind of narrowed down into this subset, I would say, of machine learning, where our intent has been mainly to create systems that can automate the whole process of learning. So now, we are talking about creating systems where you're not even really involved explicitly with creating the logic or the programming aspect of it. You just show your systems a lot of data. You kind of show it a lot of samples of how a certain task is performed, and accordingly we expect the system to kind of, understand or pick up on that relation all by itself. So post, 1990, late 90s, lots and lots of good work has happened within the machine learning domain. um, there are again various categories to ML. I think, that probably most of us have come across in literature, or in terms of real world applications as well. The supervised versus the unsupervised techniques, depending on how your data sets look like. Are you trying to teach your system, to make a prediction? Let us say you're given some data about a loan applicant and decide whether you would want to approve a loan for them or reject. So being able to automate that whole decision making process. One further improvement, or I'd say, one a more complex approach to the whole learning process itself is, when we start making use of deep learning techniques. The essential idea still stays the same. We still expect our systems to learn or uh, pick up on the learning part by themselves, but the approach to learning changes. Especially within deep learning, the learning approach, I would say, is definitely more complex. There is a whole lot more math that is involved, and also deep learning happens to be much more suitable for the more richer and unstructured data forms like image data or the natural language processing data that we keep generating heavily on a regular basis. So most of the time, I would say it's the kind of task that you're trying to perform, as well as the kind of data set that you're dealing with, that would help you determine whether you go with an ML approach versus a deep learning approach. Why do we see, all this massive increased interest around deep learning in specific, and more currently generative AI, which happens to be a much deeper subset within deep learning? One, I think all of us would agree to the massive increase in computing power that we are noticing happening almost on an exponential basis. For example, in terms of the number of operations that get carried out when a simple data set is being processed or a simple functionality is being achieved. The latest, especially over the last 6 years, the number of operations that they carry on has risen in the order of magnitude of, 10 to the power to 12 to 10 to the power of 13 operations per second. I mean, that is massive in comparison to the kind of compute power that we had, I would say, even 10 years back. One Probably, going on a tangent here, but one reason why this has become possible is also because of the massive kind of advancements we see in the kind of hardware support we get today. Nvidia, if you notice, has now risen to, the top three in terms of market valuation, mainly because they are fueling all this back-end hardware support in terms of the kind of GPU chipsets that they produce. One other very important aspect why deep learning has become such a big reality, and also the reason why we are seeing such good applications coming out from this area is because of this whole availability of labeled data. Initially, especially with machine learning systems, the amount of data that was required, I would say, was typically much lesser. But when it is deep learning that we are talking about, again, the rise in scale or the amount of data that we require goes up exponentially. And that has become possible over the past 15 to 20 years. To kind of put it in perspective, if you compare it over the last 20 to 24 years, the amount of labeled training data sets that have become available to all these huge companies, or for research purposes in terms of availability, has really gone up, again, mostly in an exponential fashion. Mm, Even if you kind of, keep looking up all the current information that keeps getting posted about the kind of training data sets that go into building tools like, let's say, ChatGPT, or the more latest versions of Google Gemini, or the image generation tools, they are probably scraping billions of videos of internet, YouTube, or images of services like Instagram, to be able to power all of their algorithms as such. Also, the improvement in terms of the kind of software and the algorithms that are now available to us, this has also been constantly on the rise, um, right from when we have started, let us say, with the essential idea behind neural networks. Theoretically or on paper, I would say, the idea behind neural networks has been around probably since 1940s or 50s. The Again, the essential idea of how a convolution neural network should perform has been there probably from 70s, but it is only around 2012 that actually implementing a really powerful convolution neural network has become possible, both due to the hardware and software support that is now available to us. Post 2018, again, massive improvements in terms of the kind of transformer architectures or the kind of generative adversarial networks that are available out there for us to start implementing on our own data sets. One final reason why we see all this, again, massive improvement, is the availability of open source platforms and tools, especially both from an academic or from a research perspective. Most of these platforms and tools have been made completely open source. So at least to get started with, the tools are all out there in the public domain. Even most of these really good architectures that we'll be discussing in a little while now are all available in open source mode, either from Kaggle or from the GitHub repos of the companies that host all of these architectures. So even as an individual, for us to get started with this domain and start implementing at least basic architectures by ourselves has become very, very affordable. Probably, the more high-end models would definitely require some amount of investment. For example, being able to work with OpenAI models, to a certain extent, they were completely free, at least for experimentation purpose. Even till 6 months to a year back, they were giving free access to their APIs to a certain extent. But now they have all been made paid. So there is like at least a basic subscription fee you might have to pay to OpenAI to get API level or developer level access. Putting that aside, there are still quite a lot of extremely powerful models that are available out there that do give you free access. So put together all of those reasons in terms of having availability of really massive label data sets, having access to all these hardware and software paradigms, and then having access to extremely good computing power, even at a personal level in terms of, our individual desktops or laptops. All of these have fueled this massive progress within deep learning. Specifically in terms of deep learning algorithms, if we notice, one of the most important algorithms that actually goes into building deep networks, that gives them that power of being able to carry out that process of self-learning, I would say, is backpropagation algorithm, which has been around for quite some time now. AlexNet was the one place where really serious improvements started happening at a very massive scale. This was the best implementation of a convolution neural network architecture that happened as part of the ImageNet competition in 2012. Post 2017 onwards, once Google started releasing their transformer based architectures, and again, most of these code bases are available fully for free. If you go to Hugging Face or pick up any of their GitHub repos, most of these architectures are available for complete free download as such. This was the place where generative AI applications started becoming a reality. And now we have these extremely powerful trained generative models that are able to give us applications in multiple modes. If you look at the latest versions of ChatGPT or Gemini, you could interact with them in text mode, you can interact with them in the speech recognition, the voice mode. They are capable of doing real time image recognition. So providing multimodal support is where we are currently at with respect to the advancements within deep learning algorithms. So that whole discussion was mostly to kind of set the tone in terms of where we have reached with respect to the advances within deep learning. But now we are kind of going to backtrack and look exactly at what it is that happens within a deep learning architecture. Having some minimum understanding of machine learning would actually go a long way into understanding what happens within a deep learning architecture as well. Um, so if we notice the major difference between machine learning and deep learning, once you have your input data set ready, and then before it is actually ready for your algorithm, whether it is an ML or a DL algorithm, this is probably the area where you get to notice a major difference. ML still requires, I would say, some sort of programmer intervention or human support in terms of extracting the features and making your data set ready for further implementation. Whereas the strength of deep learning comes in right at this stage. You just dump massive amounts of data at your deep learning algorithms, what it is about that data itself. So in terms of feature extraction as well, the task is handled directly by the algorithm itself. In terms of outputs or in terms of capabilities, again, machine learning is equally capable of doing predictions. You put in some input data. Let us say you want to classify your patient information into a set of patients who have the disease versus a set of patients who do not have the disease. Or you have a lot of customer information and you would want to segment it or cluster it. This set of customers would be interested in this set of product bundles versus another set of customers. So across both ML and DL, we do have all of those capabilities available to us. We can do regression-based tasks where we are trying to predict numerical quantities. We can equally well handle classification-based tasks where it is some sort of text labels that we are interested in. But the essential difference comes in terms of what kind of data sets are suitable for each of these kind of techniques. This next slide should actually make that a lot more clearer. When it is machine learning, we are typically looking at or we are working with a very structured kind of a data set. For example, this small snippet that we see is one part of a data set that is meant for building a diabetes predictor. So now it is the responsibility of the programmer or the ML engineer to even determine what kind of columns are needed. Probably, for understanding whether somebody would be prone or at high risk for diabetes. Definitely, age would be a factor. Whether or not someone within the family already has that condition would really have, some sort of bearing on that. So certain parameters like your blood glucose level or your insulin resistance, all of these would go a long way into determining whether or not someone has that problem. Now, being able to identify these features, being able to capture the data in this specific structured format, like we've seen in the previous slide, is still, our responsibility. Unless we do the feature engineering part of it and this creation of this structured, clean data set well, your ML algorithm wouldn't be able to give you accurate results when you implement your algorithm on top of this data. Now let's contrast this with how a data set is supposed to look like for a deep learning system. Like we have mentioned, deep learning is a whole lot more complex in the way it approaches data. It is also a lot more better at giving us all those various functionalities. So one specific kind of data set, let's say we pick up image data. If you notice the difference between both of these data sets, now for your deep learning system, you're just throwing in a lot of images. And if it is in a supervised fashion, they already have the output labels that are attached to them. Now, exactly what is it that is of interest to us? Especially as, laymen, I don't think these images would make any sense to us. To a certain extent, we can still understand what this structured data set is referring to. But when it is image data, which point or which areas or which parts of this image are really important for me to decide whether this is like a x-ray scan from someone who has COVID versus a very normal healthy patient versus someone with a slightly different presentation of the disease. So these are some things that I cannot exactly pinpoint and pick out. We expect the system to learn that part of it also by itself. So now, what I mean by this is your deep learning algorithm will also try to understand what parts of this image are really important for me in helping me decide whether someone has COVID versus whether it is a healthy scan. One very important aspect probably that we all definitely need to focus on here is, irrespective of the kind of data that we are supplying to our deep learning algorithms, at the end of the day it all gets converted into a numerical fashion. For us, it is very rich unstructured data. Let us say you pick up a device like Alexa. This is speech data that we are using to interact with the device. But for the neural network, it is the speech which is converted into those audio patterns, which is once again converted into the equivalent text, then finally converted into some sort of a numerical embedding that actually gets fed into the neural network. So for us, it is speech. For the system, it is again huge collections of numbers or numerical values. Image data. Once again, for us, probably this is a nice colorful image of a face. This does look like, it's the black and white version of Abraham Lincoln, but to the computer or to the deep learning network, it's once again a massive collection of numbers. So this image data is divided or, represented essentially through its pixel values, and those pixel values are stored in this matrix format. So this is the comparison, or I'd say difference between a black and white versus a color image. A black and white image at each pixel would consist of a single value. If you contrast that with a color image, since every color is a combination of red, green, and blue values, internally every pixel itself is a combination of three values. So this becomes like a 3 by 3 into this kind of a matrix. So it's just like a much more massive combination of numbers. But again, to the deep learning system, it's just this huge set of numbers that is thrown at the system. It doesn't look at an image and think, okay, this is the image of a face or this is image of a cat. Um, the way we humans look at it and try to recognize it. Instead, it is just trying to figure out what sort of patterns do I see commonly being repeated when I look at an image of a face. What sort of combinations of pixel values might lead to this overall bigger feature of an eye. So that is the kind of understanding that a deep learning network will be able to get. even natural language data, whether it is, some sort of system like Google Translate, where you put in your own, the kind of text that you want, let's say in English or Japanese or French, whether you're speaking to Alexa. So a lot of these, or when you're interacting with chatbots, voice bots, you are putting in data in your own natural language. Once again, this data definitely passes through some sort of an embedding model. The very end, it has to be converted into some sort of a vector or a numerical representation, which then becomes the input for a deep learning neural network. So how does this conversion happen? This is probably a completely different topic in itself. And in fact, um, one of the upcoming webinars will try to give you a little intro into how large language models work. There have been much simpler ways of carrying out this kind of word embedding that have been around from a long time, the bag of words model or the TF-IDF model. And more recently, we have these extremely powerful language models that are very good at capturing or converting this text into this sort of a vectorized representation. But that I would say is like, a completely different topic by itself. For us, the most important point of interest as of now is, irrespective of whether it is natural data, image data, or speech data, to the deep learning network, it's all huge amounts of numbers that are being sent into the network at the input layer. Okay, let's go ahead and now look at the most basic architecture of a neural network. And this is an extremely simplistic representation. Any of our real networks as such, there would be hundreds of these hidden layers in between, with hundreds of neurons also at each layer. But in terms of the basic terminology itself, you have your input layer where all of those numbers from your input data, which is basically, the pixel representation of your images, let us say, get fed in. Um, the output layer is determined by the kind of task you're trying to perform. Let us say you're trying to predict the price of a used car. So it is one single numerical prediction you're interested in doing. You would probably end up with this kind of a structure where you have one neuron at the output layer. If it is a binary classification task you're performing, let us say I want to decide whether or not those scan images that we saw earlier, for example, let me just quickly. All right. The COVID versus the healthy versus the pneumonia kind. So there were three possible outputs over there. In that case, you would have, two more neurons here, three output neurons to correspond to those three cases. So the input and the output layer are pretty much fixed depending on how your data looks like and depending on what kind of a task you're interested in performing. This is the area where you totally get to play around with how many hidden layers do I want, how many neurons do I want at each layer, what kind of activation functions do I choose, what kind of inherent calculations are happening. This is all determined by the kind of task that you're trying to perform. Also, in terms of the terminology itself, all of these round nodes are typically referred to as neurons. This is where either the input gets sent in or all the internal calculations happen within the in-between layers. All these arrows that we see interconnecting one layer with another, these are referred to as weights. Very, very important concept. All the learning that happens within a neural network is trying to find the right set of weights. And basically, when we start off with a neural network at the very first instance, all these interconnections that we see here are initialized with random numbers. To kind of make it really simple, I can just say each of these arrows here comes with some sort of a numerical value. Let us say 2 here, a 3 here, a 4 here, kind of a thing. And these numbers are chosen randomly by the network itself. And the process of learning within the network is trying to end up with the right kind of numbers. We'll look at that in a little bit now. Um, Each of those neurons does include a lot of computations that happen within every single neuronal stage as such. So there will be computations happening at all the neurons within all of the hidden layers. So this would be the basic terminology associated with a simple neural network. Let's look at, again, I won't be going into way too many details here, but just to kind of uh, bring out, the kind of math that is involved within a deep learning neural network. It's not strictly necessary for us to 100% understand what happens, but having this basic understanding will later on give you a clue as to what kind of network architecture would you want to implement for what kind of a purpose. So like we saw all those input neurons and all those interconnections that we have seen referred to as weights. So there is this multiplication that happens input neuron into weight, and then a summation of all of that, which is then passed through an activation function. So in simple terms, it is a huge number of, and when I say huge, I am probably referring to a number in the range of millions or billions of the same set of repeated kind of calculations that keep happening throughout your network. To kind of, build up that example in a more solid way. These input values and these weights, I've just chosen certain random numbers. Let's say, your input neuron weights values coming from your input data, 5, -2, -1. These are the random initializations happening for the weights. This is the bias term that goes in, and this is the calculation we need to perform. That becomes, a 5 into this, plus this into this, plus this into this, plus this kind of a calculation. So that is the calculation happening within the hidden layer neuron, which gets passed through some sort of an activation function. For example, this entire computation, which turns out to 1.9, when I pass that through a sigmoid activation function, leads to an output of 0.86. So just kind of going back to the slide. So what I showed you now was the kind of calculations that happen within any one single neuron. We had a set of 3 input weights, set of those 3 weights coming in, the multiplication happening, being passed through an activation function, and the output. So now this output, once again, inputs becomes the input for the next layer. So it is these kind of computations that keep happening at every single neuron successively at every single layer. Okay. One word as to why we use these activation functions. Very, very important concept once again within neural networks. Like we have seen in the previous slide, the output, which was this dot product kind of a thing, has been passed through a sigmoid function. And there are various varieties of functions that we can pick up. Again, this is up to the programmer who is creating the deep learning architecture. Certain kind of functions are suitable for certain kind of tasks, but why even use them? The whole idea behind a deep learning network is essentially to introduce some sort of non-linearity into the system. Um, for example, even as human beings, when we process data, let us say you are looking at certain image on the screen, there is a lot of information put in over there. There is some text, there's probably some logo here, one image here, and another bigger image here. Probably as of now, you might be either focusing on this image or maybe on one of these. We're not really taking in, all the information. There is certain text here, a logo towards the right end. But when you're looking at this particular slide, certain parts of the information our brain deems as more important and gives it or attaches more value to it, while certain part of the information, while it is available to us, this information is something we are looking at probably on every slide, but we do not pay that much attention to it. So certain part of the data we would want to highlight, and correspondingly a set of neurons in our brain are highly activated for taking in some part of the input while repressing, I would say, certain other parts of the input. This is also the kind of logic that goes into a neural network while it is trying to learn something of importance about the data. It would only a part of neurons would be activated, while certain other neurons would not participate in learning about that feature. Very quickly going back to one of these slides to, yeah, so for example, if it is trying to understand this particular image, which happens to be a human face image, and then trying to understand, the structure of the eye, only certain subset of the neurons would be involved in learning the structure of the eye, and a majority of the neurons would not even be activated. Again, a different subset of neurons would be involved in understanding the shape of the nose, whereas the first set of neurons might not really be involved with this part of the learning. So in order to introduce that linearity, which part of neurons should be activated versus which ought to be, kind of repressed or stay back at a zero, this part of the job is handled by the usage of activation functions. And for example, if it is convolutional neural networks, this activation functions works better. If it is a recurrent neural network, the ReLU activation function works better. So which function you would pick up would be determined by what kind of data set and what kind of a task you're trying to perform. So this is an animated view of the work that happens at an individual neuron. And this is actually putting it into perspective in terms of a much more bigger overall network itself. An image of three being fed into all these input layers. We have a lot of hidden layers in between. We've already said all these interconnections are called as weights. Each of them has very different number attached to it. And once it has figured out learning that this is the image of three over here, you notice, some of those lines show up in blue. Um, these are positive weights. That is, the interconnections having a very positive number attached to it, something above zero. And you have these red lines, which have a negative weight attached to them. Essentially, all learning within a network is the process of starting off with a random set and trying to identify the right set of weights. A very simple analogy here, for example, if a student has spent 3 hours of studying and 7 hours on social media on a given week and ended up with a score of 70, wants to get to a score of 80, what can she probably, or what can the student do? Maybe increase studying, decrease social media. You see a difference in the final output. Make one more change here. Maybe, increase that study massively, decrease social media a lot. That is leading to your desired level. So if we think of these numbers as weights, certain weights you would want to increase, certain weights you would want to decrease. And over here, a little math does come into play, especially calculus and partial differentiation, how you would modify that weight. And like we have seen on one of those earlier slides, there are probably a billion weights that go into even the smallest neural network architecture. And the more recent ones typically deal with billions of those weights that they have to learn optimal values for. And this is where the backpropagation algorithm comes into play. So it starts off with some random values, like it's shown in orange here, figures out how they are different from what you actually want to get at, and takes that into account to back propagate the error and modify the weights. I'm kind of, doing that at a very fast pace, but that's just to kind of give you an overall idea of what happens within a deep learning neural network. Now, moving on to network types and applications. We are going to talk about two specific flavors for today. One is the convolution neural network, and another is the recurrent neural network. Now, wherever we are dealing with image data, you can be guaranteed there is a CNN working in the background. So, where it is your image data, which is once again converted into this pixel form, especially with image data, we have to have this additional operation called as convolution, which helps us understand that image data. Again, like we said earlier, for us, this is the number three. For the network, it's just this massive calculation of pixel values. How does it figure out that there is a straight line here and a curve here? For that, it will have to use this convolution operation in order to figure out those features. I'm just going to stop with the slide share for a minute here, and I'm going to go to this a working demo of a convolution neural network?
But I will still see the slide just so that
Yeah, I'm just going to, yes, thanks, Raj. Yeah, it should be coming up now.
Yeah, deep lizard.
Yeah. So this is, extremely good working demo of what or how a convolutional neural network actually works. Let's say now I'm picking up one of these data sets called as the fashion MNIST data, which is images of various fashion or clothing based items. I'm picking up a bag image. You'll see towards the bottom the pixel equivalent of a handbag kind of a thing. And when we say convolution, these are all the different sorts of convolution filters that are available. You see a list of some 10 over here. In a proper CNN network, there would be thousands of these filters that are actually applied on your data to learn about various features. Where are the edges? Where are, the right left columns or the right curves? All those small, minute features about your image are being learned through all of these different filters as such. So I pick up any one filter and, if I use the step function, this is the output that is being generated. If I click on this play here, that's the overall output that is being generated. So essentially, it is matrix multiplication, thousands of them happening on a continual basis, and each filter learns something of interest about that specific image. Again, the blues, where there are some sort of here, the blues are the negative activations, and the orange is very high positive activation. We pick up a different filter, it is going to learn something different about the image itself. Stopping share there. So that would be the essential idea within a convolution neural network. Let's talk very briefly about the applications part of it before we come to the end of the webinar. Again, the amount of time, frankly, for deep learning, just the idea behind a deep learning itself, we could do for like an entire day in detail. We just trying to give you an overview of exactly what it is that happens within a deep learning network and what are the various types of networks available for us. Okay. Talking about the various applications of convolution neural networks now. My slides are visible, right? I'm on the facial recognition slide.
yes.
Yeah, thank you. Okay, so in terms of any of those CNN applications, like we said, CNNs are perfect for image, being able to recognize faces, whether it's a surveillance system, whether it's your, you know, phones that are doing unlocking based on your facial detection, um, whether it is Instagram tagging your pictures, all of these are making use of facial recognition. This is latest, cutting edge research. This was only published a couple of days back, research from MIT, where they have done um, image analysis on mammograms, and now they are able to figure out risk for breast cancer 5 years before it even starts developing. This is huge or massive in terms of the kind of health benefits that are possible. Self-driving cars, obviously figuring out what is in front, being able to do that object detection in real time, accordingly modify its behavior. A lot of these creative applications, being able to do style transfer, creating or generating really new cool kind of animations based on existing data. Automatic document analysis, coming up with image captions. So wherever it is image data involved at the backend, we are dealing with some sort of a convolutional neural network. Going forward, another flavor of network, very famous again for speech and NLP data, is the recurrent neural network. Systems like Google Translate, you put in something in English, the recurrent neural network processes the entire data, converts it into that target language and shows it back to you. Being able to do sentiment analysis, for example, again, processing a lot of NLP data, figuring out what kind of terms come in there, are they positive or negative in nature. All the chatbots that we interact with, either voice or speech, the chatbots we interact with on apps or websites, the typed ones. This feature of autocomplete, whether it's on your phones, even in like systems like WhatsApp or your emails that are helping you with the autocomplete, being able to do time series forecasting, stock price prediction, rainfall prediction. All of these are really good use cases for RNNs. There are still certain challenges in terms of deep learning, availability of data, massive amounts of computing that are required, to process all those huge amounts of numbers that we saw. Lots of energy requirements. Companies like OpenAI are now consuming more energy than small countries put together, in fact, in terms of their electricity consumption. Being able to come up with even more optimized and efficient architectures that can finish up all that training in a lesser amount of time. So these are all still working areas within deep learning. And current, if you will have to guess which of these is real, some of you can probably put that in the chat, whether it's the image on the left or the right, which is a real image versus a generated image. Current focus, although right now, is in terms of generative AI based systems, and these make use of much more specialized deep learning network architectures like the GANs and the transformer based architectures. But that's kind of topic for another day. And this is my plan for today, to kind of very quickly showcase what DL is, what happens within a deep learning network, and what are certain flavors of networks and applications that we are already using from those kinds of network architectures. So I'm going to stop the screen share for now, and we can take a little time in terms of answering any kind of queries.
So if I'm not sure sharing the right screen. Thank you, Aparna. This is really great, covering a lot of deep learning. It's a very vast and deep topic in a very brief period of time. Folks, if you have any questions, please put in the chat. I did go ahead and put some links in the chat. So what we really try to do is put some public trainings as well. As I said, we focus a lot on the corporate trainings, but we do put out certain public trainings, and people take this and continue a short, quick overview. If your company provides you training funds or something, like, you can easily utilize that to get some deeper understanding in these kind of programs. A lot of on-demand programs as well. So I've shared those links. We also have a lot of these meetup groups which you can join. Some of you have definitely come from that, but if you are new and join to other sources, feel free to join the community, and then you have access to whichever different meetup groups. So that link's there. As I mentioned, these videos will be shared on the YouTube channel, and the link of that has been provided as well. And you see previous recordings of several topics, so feel free to browse through that and explore. We do a lot of e-learning, and there are different programs in that perspective as well. You can explore that. All the webinars and recordings and things are posted on this link. So all these links have been shared in the chat. And so that's pretty much in terms of content. Let me see if any questions. Yeah, so I think there was a question whether I missed some of these great talks. Can you share the recording with us? Absolutely. So I think the recording, I think I'll put all these links. I think maybe if you join later, I'm just going to put all the links for everyone again, so that everybody gets access. And the YouTube link is where the recording are, so you have access to that. Feel free to look in the previous ones in the pages provided. Then we have other question or comment. Okay, great. Thank you, Arlene, for the kind comment. Yeah, it was very well structured and quite a deep topic, though, I think, but it's a very important topic. People don't realize a lot of the AI and generative AI things are happening are stemmed from deep learning, and that is playing very, very important role in several use cases and patterns as we progress and harness the power of AI. So those are a couple of comments. Any other questions? Feel free to put in. I'm going to stop the recording at this point of time.